Hi everybody, welcome back to Applied Coding. In today's episode we're going to talk about genetic algorithms. More precisely, we're going to see how we implement the genetic algorithm that will learn to play the snake game. In previous episodes I talked about the snake game, an implementation I wrote in Java, and about a neural network class that I'm going to use this time. I'm going to put a link up here somewhere to see that video in case you're interested. The idea with the genetic algorithm is that you don't need to have training data for your neural networks. Basically, you just run the population and the individuals, in our case, the snakes in the snake game, over and over again. And for each run, you select the top performers, you breed them, and you create a new population for the next generation, which you run in the next generation again, and then you repeat the process. By performing these kind of selections, crossovers, and mutation when you create a new population, you basically ensure that the genetic algorithm will somehow evolve and somehow perform a optimization of the neural network. Selection is the stage of a genetic algorithm in which individual genomes are used from a population for later breeding. What this means basically is that once we have a population of snakes, in our case, which have each a neural network, which is basically the brain of the snake, we're going to select a number of snakes after they all executed a game. And we're going to see what is the top performer snake, and we're going to order them according to their performance. This means we have to have some kind of function that tells us how well a particular individual in a population performed. This is called a fitness function. So, according to the fitness function, in the selection process, we take the top, 10%, for example, of the individuals, and we select them to be part of the next generation. The way this works is that we're going to create a new generation of snakes, of neural networks, but we're going to keep these top performers. We're going to put them into the new population, and we're going to fill the rest of the population with variants of these top performers. How we do that, we see in this section called the crossover. Basically, the crossover in a genetic algorithm means that we are recombining the characteristics of existing individuals in a particular generation. There are several ways of crossover. The idea is that once you have two parents, we need to take the characteristics of each parent and somehow splice them and recombine them so that we create a child from those two parents. In the snake problem here, I chose to take the two neural networks of the parents and to basically just choose a random point in those neural networks and take the first part up to that random point from one parent, and then to take the second part from that random point until the end of the neural network from the second parent, and then combine them together and put them into the child neural network. Finally, the third operator we're using in a genetic algorithm is the mutation. Mutation is basically used to maintain diversity from one generation to another. The idea is that since now we have crossed over two parents and created a child, there is no new information in that child. It is the same information, the same neural network, basically, if you want, only spliced and recombined from the parents. That's why now we use mutation in order to get new characteristics into the properties of the child neural network in this case. When we are performing mutation on a neural network, we need to do that with a certain probability, a low probability, and when the change happens, it will only change the existing value by a little. We're going to give probability of change and size of change of a particular weight and bias in the network. We'll see this in more detail as I'm going to talk about the code. Okay, let's have a look at the code now. I have a genetic algorithm class here, which contains a variable called games, which is basically a list of games. This game class basically represents one game of the snake game that has executed, and we have game statistics in it. We know how far the game went, how many fruits it ate, so we have the state of the game. But more importantly, we have a neural network in the game. This is the neural network that was used to control the movements of that snake. In the genetic algorithm class, we have this evolve method. This is a method that we call once all the snakes, all the games in that generation have finished. So we have a score for each of those snakes. We know how far they went and so on. And now we need to see how we evolve the game, the population. So first we need to do selection. We have a list of games, and we need to select those 10% of those games that perform the best. How do we do that? So we need to look at something that is called the fitness of each game, the fitness of each snake. That's why we are sorting this list according to a fitness comparator. Just quickly look at this fitness comparator is just looking at two games, game 1, game 2, taking the fitness of them and then returning whether fitness 2 is greater than fitness 1. The way we do this is we look at the game state and the fitness function in that game state. So let's have a look how this was implemented. The idea is with the fitness function that we are going to evaluate how far the snake has reached in the game, how fast it reached certain items, for example, the food, how quickly it died, how many steps it made, and so on. The idea is that we need to be able to quantify if the snake has performed better than other snake. Now, I implemented two fitness functions, one geared towards exploration and one geared towards optimization. The idea for exploration is that in the beginning, the snake has no idea what it's doing. It sometimes ends up just circling in a loop because it believes that that is fine, that's good enough, because it scores points for just moving around and it doesn't die. But doesn't optimize a particular problem. So that's why in the beginning when a snake is not experienced, the neural network is not trained very well, I'm using the first fitness function, the one for exploration. This one basically it rewards the number of steps the snake performs. So the more steps it makes, then the better the fitness function. Now the second function is then again for snakes that have been trained, for neural networks that have been trained already, and it rewards quickness in finding the food items. Okay, now that we have sorted our parents according to their fitness, we are able to take then the top parents from this generation. Now, also part of the selection, it's an algorithm called a roulette selection, which basically needs to tell us how do we select, which parents out of those 10% do we select, because they're not equal. They still have different fitness functions, and the top parent has the best fitness function, and as they go down, they have lower fitness functions. For example, in this loop, we're going to select a dad using this roulette selection according to their fitnesses. We're going to select the neural network of the dad. We're going to select the mom, and we're going to take the neural network of the mom. Once we have the two neural networks, dad and mom, then we can do the crossover and the mutation. So let's stop for a second and talk about this select roulette. The idea is that we need to we still need to select the parents that have larger fitnesses more times than another parent which has a lower fitness. There is a very nice algorithm called the fitness proportionate selection, which takes care of selecting parents more often, those that have a higher fitness function. Enough to say that the implementation in Java is this one. We're basically going to take the parent that has a particular fitness more often than other parents who have a lesser fitness sum. And now we move on to the crossover. Now, as I mentioned before, the crossover is when you have two parents and then they have two characteristics, two genomes, they call them in a genetic algorithm. In our case, the genomes are basically the neural networks, so we need to combine them and form a third individual. This will be the child. But the idea is that we take the dad neural network, we cross it over with mom's neural network, and what we get back is a third neural network, which is the child neural network. Once we have the child neural network, then we set it into the population. So basically, I'm not creating, in this case, a new child snake game, but in the child snake game, we set in the new neural network. So we give that snake a new brain, basically. Let's see how this crossover is implemented. This is done in the neural network level. So this is part of the neural network class that we talked about in the previous video. Again, I'm going to put a link up there somewhere for the previous video where I described the neural network. But what happens here basically is that we create a clone neural network based on this. And what we're trying to do then is we're going to compute out of each hidden layer. We're going to compute a point because they're matrices. These hidden layers are matrices with weights and biases. So we're computing a point in the matrix where we're going to copy the first half to that point from one parent, from the dad in this case, and from that point further to the end of the matrix from the other parent. And this is how we create now a new neural network, half of it or part of it from one parent and part of it from the other parent. So that's why now here we're computing this crossover point, which is a random point in that weight size, so which is the rows and columns of the hidden layer. And in the for loop, from that crossover point until the weights size, we're going to copy over the weights from the other weights matrix. So initially we have the weights from the parent, from the dad, because they were copied over in the copy constructor, and from a certain point further, we're going to cross it over and copy it from the other neural network, from the moms. Now, this basically gives us a third neural network, which is a combination or a recombination of the dad and the mom neural networks. Finally, we arrive to the mutation point. We need to put in new information in the child neural network so that there is going to be some freshness in the neural network. It's not just recombining existing parts. And what this mutation does basically is we're going to mutate the kid neural network according to a mutation rate and a mutation strength. Basically, we are now again in the neural network class. In here, we have this mutate method, which has a rate and the strength. So what we need to do basically is we go through each hidden layer of that neural network and through each bias layers from the neural network, and we're going to take the weights. For each weight, we're going to iterate all the weights matrices, and for each weight in part, we're going to check if the particular random number is lower than the rate. Then we're going to mutate the existing weight. We're going to add to it a random Gaussian multiplied by the strength. So this strength typically is, let's say, 10% or 1%. So we're going to change the existing value of that weight by a random number multiplied by the strength. So it's going to be just a tiny change basically of that existing value, either in the positive or in the negative, because random Gaussian could be either positive or negative. Then we do exactly the same for the biases. Biases is not a matrix, but just a column or an array in this case. We just go through all the biases, and if a particular random number is smaller than this rate, then we're going to adjust the bias at that position, again, by a random Gaussian multiplied by a strength. One interesting thing to note here is that what would be a normal mutation rate? For example, I have created this get default mutation rate method for a neural network, which returns a double. So basically this gives us the probability that a particular random number has to be under in order to perform a mutation. So the way you've seen here, this rate here, a particular random number has to be lower than this rate in order to perform a mutation. Now, what would be this rate typically? Well, a default mutation rate is basically the chance that an item in a particular neural network is likely to change. So if a neural network has many hidden layers which have different sizes and it has biases and so on, then the mutation rate, the default mutation rate, gives us the probability of one of those items in the hidden layers to change. So in mathematics, we calculate this by looking at how many items do we have in the neural network, how many weights do we have in the neural network. We sum up all the number of the weights, and we count all the biases. So once we have all this, then we basically divide 1 by the total number of weights, by the total count of weights, and that is the default mutation rate. So just to note here, this is not the sum of the weights, it's just the count of the weights. And just to make another note, this is just a default mutation rate. You don't have to use it. You can use higher mutation rates or lower mutation rates. This basically will make your genetic algorithm learn and evolve faster or slower. The problem is that if you evolve too fast, you will skip certain steps in the optimization, and you might not find the actual local minimum or local maximum, whatever you're trying to find in your genetic algorithm, but you will skip it because you made too big of a step. So it's always better to use lower mutation rates than the default. But anyway, we'll see this in a future episode where I'm going to show you how to run this entire neural network and genetic algorithm on a population of snakes, and we're going to see how they evolve and how fast they evolve, what types of snakes evolve faster than other, what type of inputs of a certain snake perform better than others, and so on. But all this in a future episode. This is pretty much all I had for today. So If you find this content interesting, then please give it a like, and I would really appreciate a subscribe. And I'll see you in the next video. Until then, bye bye, have a good one.